Alright, welcome back. You are hanging in there, and that's awesome. Okay, so we are doing ideal gas law stuff. If you've got your packet, you are on this page. And we're going to start from the top. Things that make this particular page a little bit tricky are that all 4 of these questions go together. So every once in a while, somebody gets to question 2 and they're like, I can't solve this, I don't have enough stuff. If you're missing anything, find what you're looking for in the previous question. So like, it's as if this is all one big question, basically. Your favorite, right? Okay. Off we go. You will, of course, also notice that the page is numbered wrong and has typed at the top. Oh, I should really mention this. If you are getting this page from the Google Classroom, awesome. The first and potentially most important thing that you are going to do on this whole page is correct their mistake. It just occurred to me that I'm using a computer and I could do this for you. I'll just do it for you. The mistake you would have corrected is this one right here. This number is R. I'll correct that for you. Great. We don't have to worry about that anymore. Okay. Off we go. Let's do this. We got a gas cylinder with a volume of 108 liters. A lot of this is going to look real similar. You're going to do your setup just like you always have. You know what? I should read your question before I start that. Okay. Gas cylinder has a volume of 108 liters when it's filled with 22,700 grams of nitrogen gas. If the temperature of the cylinder is 25 degrees Celsius, what is the pressure inside the tank? Things you might notice. You might notice that there's no change of state. We don't take this up in a hot air balloon. We don't put this in the oven. We don't leave it in a hot car. It's not outside during a storm. There's no change of state. We're just saying that this container has this volume and, you know, these characteristics. We're not changing it. Anytime that there's no change, I should have mentioned that before. If there's no change in your question, then you use the ideal gas law. If there is a change and you have an initial state and a final state, that's when you're going to use this combined gas law. But if there's no change of state and you're looking at a balloon on the surface of the earth, just it is what it is, that's when you're going to use the ideal gas law. Alright, so there's no change of state here. Let's do it. You know, okay, so this is ideal gas law number 1. 3 parts to this question, as there have been 3 parts to all questions. Part 1 is your setup. You know the variables you're looking at. We've got some PV and T. These are the ones that you are really good and used to. We added in N, number of particles is N, and R. Again, this is the last day of the gas laws. There's no like 6th variable that's coming at you later. Okay, so your volume is 108 liters. When it's filled with 22,700 grams of nitrogen gas. You have to know which variable grams is going to be talking about. Maybe let's narrow it down a little bit. So we've got a temperature of 25 degrees Celsius. And we're going to solve for pressure. I'm going to get orange so that I can write those and they will actually show up. Can I have orange? Anything kind of like an orange? Kind of pink. Okay, I'm going to try some colors. Okay. Red. Let's go with red. pressure is now red. Hopefully that will show up. Yeah, that shows up, right? You can see that. Okay, pressure is now red. So we're going to solve for pressure because this question says, what is the pressure? That's our question mark. Okay, so we now have identified that we are given volume and temperature and solving for pressure. And then there's this grams deal. One thing that you want to kind of know in your own mind is that if you're that grams deal, you can convert that. Yes, you can. You can convert that to the unit that you want to describe how much or how many. So we have 22,700 grams of nitrogen gas. Here's a pro tip. Nitrogen is N2. Okay. This one has an extra step. Here's the extra step. We're going to convert this from grams into moles. You've got yourself a molar mass. You want to find how many grams in 1 mole of N2. This is a good one to do together. Not, like, many of them will not have this step. Like, many of them will just tell you moles, and then you're like, moles, that's all I want. Great. This one has this extra bonus step. But we're doing it together, so we're cool. Okay. N2 is 2 nitrogens. Each nitrogen is 14.01 grams. Do I still have my periodic table somewhere in this pile of mess? I should really clean my desk. Help. Or we could just, hey, I found it. Like, we could just take my word for it. So nitrogen, 14.01 grams per mole. It's twice its atomic number. And I just happen to remember the 0.1. If you're like, how do I memorize all the atomic masses? It doesn't work for all of them, but kind of the smaller non-metals up in that corner, it does kind of work for. Anyways, okay, so that's the molar mass of 2 nitrogens, and nitrogen's diatomic, so that's what we want. Numbers follow their units. This is a flashback to week 3. Okay, grams are on the bottom. We're canceling out grams. We started in grams, but we're going to get rid of them. That 28.02 goes with the grams. And it's that many grams per 1 mole. If you are looking at this and confused, look at Wednesday of week 3. So the lesson of Wednesday of week 3. And that'll get you some more grams to mole conversions. Okay. But now we've got it set up. 22,700 grams of N2. We want to find out how many moles, because what we actually want is number of particles. 22,700 divided by 28.02. Alright, so we have got 810. Yeah, 3 sig figs, we'll take it. 810 moles of N2. This one does have an extra step. Okay, so that is the number that we're actually looking at. Volumes in liters, we like that. Temperature is not in Kelvin yet. Plus 273. And that's going to get you 298 Kelvin. Getting ever closer. There's only 5 of them. PV, NR, and T. And R is a constant. R is that 8.314 kPa times liters divided by moles times Kelvin. Okay, that's your setup. But setup is often the most laborious of your 3 steps. For your second step, you're going to find the equation that you want. You are solving for pressure, that's your question mark. Here's your equation page. There's solving for pressure. You could of course do this in your head as well. Divide both sides by volume, nRT over V is going to solve for pressure. Or you can pick it up and copy it. Totally your call. P equals nRT over V. Here's the step where you get to feel real cool because you're going to write like a million numbers and you're going to be 100% confident and 100% right, and it's going to take you like no time at all. And you're going to do this because your setup is already perfect. Off we go. You want on top, you want nRT. There's your N, 810 moles of N2. Here's your R. This is the main new thing that you've got here, 8.314. So R is on the top of the fraction. So we're going to put 8.314 and the units, kPa times liters, on the top. And on the bottom, we're going to put those units that are on the bottom of the R, the mole times Kelvin. All that pink stuff is R. Yeah. So we've got N is right here. R is all the pink stuff is R. Here's your temperature. Pull your temperature from your setup. We just picked that up and plunked it in. There's your N, there's your R, there's your T. You're just looking for your V. Your V from up here, 108 liters. See, you did all this setup noise that took forever so that when you got here, it was actually that easy. Okay, so in your final solving step, you are gonna punch these things into your calculator and check the units. Let's do the units first because we can. Off we go. We have the unit of mole on top, mole on the bottom. Thing divided by itself is 1. We have liters on the top and liters on the bottom. Thing divided by itself is 1. Liter, the unit of liters cancels. We have Kelvin on top, Kelvin on the bottom. The unit of Kelvin cancels. And we are left with the unit of kPa, which we're going to use to solve for that pressure. It worked! All those crazy units worked. 810 times... Okay, so here I'm just doing the math. I'm just punching numbers into my calculator. On top I have 810 times 8.314 times 298 equals, huge number, divided by 108. That's a really big number. What? Wait, is that right? That seems huge. We're gonna do a little logic check here, and then we might even check the math because this number is really big, and apparently I'm writing it in pen. That's great. Okay, I'm getting 18,000. Okay, I'm just gonna write all this stuff because there's no reason why I'm writing all this stuff. I will put this. I'm 100% confident in my unit. Okay, let's just sig fig this because this is going to drive somebody nuts, which is great. Okay, so we're starting with 3, 2, 3. This is a constant. Okay, so we're going to keep 2 sig figs here. Both of these are valid answers. That's a comma. Okay, we're gonna do a little logic check here just to make sure this is not super crazy. But I think that's actually right. Yeah, that's... I'm just looking at numbers now. Let's also, the other thing that we can do, if we're really curious, we can convert this to atmospheres. 1 atmosphere is 101 kPa. So let's just see how many atmospheres are in that tank. 183 atmospheres. That seems 0.9, so that would round up to 184. It seems like a lot of atmospheres, and with your sig figs, that's 180. But I mean, it's a container of gas. You can get that many atmospheres into a metal container without popping it. There's no way you could get that much pressure into a latex balloon. You would pop the balloon, but a metal, you know, those metal gas containers, it could hold that much pressure. Cool. So this is your example. I will, of course, come back and correct myself in case I've done something wrong. I will check it, because that seems huge. But, you know, even if your number seems really weird, go with it. Like, go with what your numbers say. Yeah, in this class or, like, out in the real world, if you're reporting data, report your data. That is, like, one of the key things you can do as a scientist is, like, not lie to people. Let them know what your numbers say. Check them. Make sure they make sense. But then, you know, present them truly. Okay. That's your example. You are going to do the rest of this page. Yes. Things that you need to know about this page. So if we increase the temperature to 85 degrees Celsius, keep everything else from part 1 the same. So you're going to do the same equation actually with 85 degrees Celsius instead of 25 degrees Celsius. I just realized that they didn't even write Celsius here. This page apparently has a lot of typos. How did I know with total confidence that that was Celsius and not Kelvin? 2 things. 1, 25 Kelvin is almost liquid helium, incredibly low temperature. Pretty close to the temperature of outer space. Very cold. Not something you're going to hit on Earth. The other thing is that degree sign, we only say degrees Celsius, we just say Kelvin. There's no degree Kelvin. Those are my 2 clues. They should say Celsius. Okay. So that will take you through question 2. If we decided to replace the gas inside the tank with 2,700 grams of O2, oh, they give you the formula. You're great. You've got 2 oxygens. Oxygen's diatomic. What would the pressure be at 25 degrees Celsius? Oh, they're missing a Celsius there too. Great. You can solve that. You know how to do that. If the tank bursts at a pressure of 1,250 kPa, how many moles of oxygen would we have to place in it at a temperature of 32 degrees Celsius to cause the tank to burst? Okay, so here you're solving for number of moles. If you know the pressure and the temperature and the volume from back up here in number 1. So the same tank. All right. Feel free to come back with questions or email with questions. I'll post the full answer key on Monday. Good luck.